Okay, so we're back for part 2 of the video lecture on section 3.5. We're still working with linear systems. We're still talking about eigenvalues and eigenvectors and the corresponding solutions that we can build. We know that for a 2 by 2 matrix A, its characteristic equation is going to be a quadratic equation. What we're going to look at today is, or now, is what happens if that quadratic equation has a repeated root. So I'm just going to give you two different matrices here. Let's suppose I had A equals -2, 0, 0, -2, and B is going to look fairly similar, but I'm going to put a 1 in that position instead. Okay, so if I were to look at the determinant of A minus lambda I, that would be the determinant of the matrix -2 minus lambda 0, 0, -2 minus lambda, and that would equal -2 minus lambda squared. Okay. Now if I take a look at the determinant of B minus lambda I, that's going to be the determinant of -2 minus lambda 1, 0, -2 minus lambda. I get exactly the same thing. I get -2 minus lambda quantity squared, because it's just this diagonal minus this diagonal, which is still 0. So the fact that there's a 1 there doesn't change the characteristic polynomial. So that means for both of these, the character equation is -2 minus lambda squared equals 0. So there's one solution. It's lambda equals -2, and we call that a repeated root for this quadratic equation. Okay. But these two matrices are very, very different, because when I go to solve for the eigenvectors, this I'm counting as an eigenvalue twice. It's a repeated root, but that doesn't necessarily mean that I'm going to have two independent eigenvalues, or sorry, eigenvectors. Okay. And in this case I will, and in this case I won't. So let's see if we can't find the eigenvectors that go with this eigenvalue for both A and for B. And then we can talk about how that affects the general solution and how that's going to affect the phase portrait. Okay, so if I look at finding eigenvectors for A, I'm looking at A plus 2I times V1, V2 has to equal 0, 0. Now if I look at A plus 2I, it's the 0 matrix. It has a 0 everywhere. Okay. So the system of equations I get is pretty silly. 0 copies of V1 plus 0 copies of V2 is equal to 0, and 0 copies of V1 plus 0 copies of V2 is equal to 0. Every possible choice that I could make is going to work here. So every vector is an eigenvector. Now, in order to find my general solution, I just need two that are independent. So I need to pick two that are not 0 and are not multiples of each other. I'm probably going to pick V1 equals 1, 0, and V2 equals 0, 1. Awesome, I have found two independent eigenvectors to go with my eigenvalue of -2. So I've got enough information here to build the general solution. Okay. But let's take a look at what happens with B. If I look at B plus 2I times V1, V2 equals 0, 0, B plus 2I is going to be 0, 1, 0, 0. So remember, B was -2, 1, 0, -2. So when I add 2 on the main diagonal, those become 0, but that 1 is still there. That many copies of V1, V2 has to equal 0, 0. So my corresponding system of equations is nothing plus v2 has to equal 0, and then 0 copies of v1 plus 0 copies of v2 has to equal 0. Okay. So the second equation is always true, but the first one tells me that v2 must be 0. Okay. So I can choose as an eigenvector here, I could choose 1, 0. I could put any non-zero number there, but I'm not going to find a second independent eigenvector. So this one, I don't have enough information based just on the eigenvalues and the eigenvectors to be able to piece together a full solution. Okay. So this one's a little bit trickier to deal with. Let's put this one on hold for a moment, but I just wanted you to see the two possibilities that we could have when we have a repeated eigenvalue. I will also point out, in this case where we got two independent eigenvectors, remember A was just 2, 0, 0, 2. That's what we call a diagonal matrix. Okay? That's actually the only way with a 2 by 2 matrix that you can have a repeated eigenvalue with two independent eigenvectors, is if you have zeros here and the eigenvalue here. So it's totally fine if you look at that and you say, by inspection, the eigenvalue is 2, and every vector is an eigenvector. Because notice, this is just 2i, so multiplying by 2i is like multiplying by 2 in the identity matrix. It's like multiplying by 2. So every non-zero vector is an eigenvector, and you actually don't need to go through this work in order to prove that. Okay, so let's see if we can't write up our general solution now, and then see if we can piece together the phase portrait for A. We'll come back to B in a later video because that's the more complicated scenario. But for A, I can say that my general solution is just going to be y is equal to A copies of e to the negative 2t times 1, 0 plus b copies of e to the negative 2t times 0, 1, which is just a e to the negative 2t 0 plus 0b e to the negative 2t, which is just, that's an a e to the negative 2t, b e to the negative 2t. So notice we're saying x is a e to the negative 2t, and y is b e to the negative 2t. Okay. If a or b is 0, then we're talking about a straight line solution that's consistent with the axes. If they are not 0, actually let's just say if a is not equal to 0, then I can say e to the negative 2t is equal to x over a, so y is equal to b over a times x. We just have a line through the origin whose slope is b over a. Okay. The only time I can't do this is if a is 0, and of course if a is 0, then we're just talking about x being constantly 0, and we're talking about being on the y-axis. Okay. So that's what my general solution looks like, and that tells me that I'm getting nothing but straight line solutions. Every single solution in this case is going to be a straight line solution. There's no curvature at all to my solutions to this particular differential equation. So if I draw the phase plane, there's my equilibrium solution. Remember we said every non-zero vector was an eigenvector. So that means every line through the origin is going to correspond to a straight line solution. And I just need to look at the fact that, oh dear, I think I wrote 2. I apologize, I should have been writing negative 2's here. I misremembered what A was. Our only eigenvalue was lambda equals negative 2. So if lambda is equal to negative 2, then every solution is a straight line solution approaching the origin. These are the ones that correspond to the particular eigenvectors that I chose. Remember, I chose 1, 0, and 0, 1. And then I would just want to say every other straight line solution every other straight line is also a straight line solution. So that's what my phase portrait would look like. If you have a scenario like this, you'll basically get the straight line solutions that correspond to the eigenvectors that you chose. As usual, those divide the plane up into 4 regions. In this case, it was the 4 quadrants. You're going to draw a representative solution curve in each of those regions. It just so happens that those representative curves are also going to be lines. Okay. And of course, if our eigenvalue had been positive, then instead of all of these lines approaching the origin, they would all be moving away from the origin. Okay. So here we can classify this once again as a sink. Okay. I should mention we didn't classify our the origin last time, but if solutions are approaching it, we didn't because it wasn't. Sorry, flubbing the end of the video. Not going to reshoot it though, because it's the end of the video. We didn't classify in the case that we had 0 as an eigenvalue, and that's because it was not a unique equilibrium solution.